Effect of the inductance and the resistance of the RL series circuit on current growth and decay. To study this effect, we use two experimental simulations. The first simulation studies the effect of the inductance of the coil on the growth and the decay of the current. Consider the first circuit. This circuit includes a functional generator which provides a square wave voltage of frequency 500 Hz, a resistor of resistance 80 ohm. In this simulation, 20 ohm represents the internal resistance of the coil and 10 millihenry represents the inductance of the coil. The graph shows the voltage across the generator and the resistor as functions of time. Let's start the simulation. We notice that the steady state is attained at t equals 0.5 millisecond, and the maximum value of UR is 8 volt. That means the maximum value of the current is given by UR maximum over R, UR maximum equal 8 volt, and R equal 80 ohm, then I maximum is equal 8 over 80, which is equal to 0.1 ampere. Now consider the second circuit. This circuit is identical to the first circuit, except of the inductance of the coil. In this circuit, L is equal 16 millihenry, greater than that in the first circuit. I will repeat the simulation, but now the graph will show the voltage across R in the two circuits simultaneously. The blue curve represents UR in the first circuit where L is equal 10 millihenry, and the green curve represents UR in the second circuit where L is equal to 16 millihenry. We notice that in the second circuit corresponding to the green curve, the steady state is attained at t equals 0.8 millisecond, and the maximum value of UR remains 8 volt, so that the maximum value of the current also remains 0.1 ampere as that in the first circuit. So we can conclude that when the inductance of the coil increases, the time needed to reach the steady state increases, and this inductance does not affect the maximum value of the current. Now, the second experimental simulation studies the effect of R on the growth and the decay of the current. The first circuit is identical to that in the previous simulation, so that the steady state corresponding to this circuit is attained at t equals 0.5 millisecond, and the maximum value of the current in this circuit is I equals 0.1 ampere. Consider the third circuit. This circuit is identical to the first circuit, except the resistance of the resistor. In this circuit, the resistance of the resistor is equal to 50 ohm, which is less than that in the first circuit. The graph will show the voltage across R in the two circuits simultaneously. Let's start the simulation. The blue curve represents the voltage across R in the first circuit where R equal 80 ohm, and the dark red curve represents the voltage across R in the second circuit where R is equal to 50 ohm. We notice that in the second circuit corresponding to the dark red curve, the steady state is attained at t equal 0.7 millisecond, and the maximum value of the voltage is equal to 7 volt. So the maximum value of the current is given by 7 over 50, which is equal to 0.14 ampere, which is greater than that in the first circuit. So we can conclude that when the resistance of the RL series circuit decreases, the time needed to reach the steady state increases and the maximum value of the current increases.